what I was telling briefly is that uh, I was discussing about why we have to study mechanical metallurgy. Okay, so mechanical metallurgy usually deals with how the material responds with different loads and different conditions. Okay, and one more thing why we have to study is because we should know which type of material can be used in what application. Okay, and now we are discussing about the mechanical properties. Those are strength, stiffness, ductility, and fracture, and all these properties can be taken out or studied with the help of the mechanical testings. Okay, so the mechanical testings is something that is to be known. Okay, so you have to study about the different types of mechanical testings. So once I'll explain what are the different tests available, and then we'll come back, we'll discuss one of the tests in this lecture, and then come back how can these mechanical properties can be studied using that. So firstly, you have to know what are all the different tests available, or what are the different loading types. Okay, that means we use different types of loads, okay, in order to check the properties. Okay, so the different types of loadings are tensile, tensile loads, compressive, and uh, shear. Usually we have many other things like torsion, bending, all the stuff, but the main type of loads are these three: tension, compressive, and shear. Okay, today in this lecture we'll briefly study about the tension tensile loading, which we usually call tension test. Okay, so we'll look at that. Before going there, okay, before going, we have to discuss about some particular um, things. Oh, I think, is the writing visible? Someone's messaged me actually. Yeah, just a minute. I'll just do it again. Yeah, fine. Now it should be fine. Yeah. So before going and dealing with the tensile test, as I said, we have different types of deformations available. So we'll discuss what are the different type of deformation. First of all, you must know what is a deformation. So usually deformation is something which changes the shape of a material. Okay, maybe permanently or till that particular time. So we'll discuss what is deformation, what are the type of deformations. So as I said, deformation is nothing but shape change. Deformation is nothing but shape change. So we have different types of it. The first one is elastic deformation. The second is plastic deformation, and there is one more deformation which many people don't know, that's called viscoelastic deformation. Okay, so these are the three important deformation types that we are going to discuss. So what is elastic deformation? So elastic deformation explains us that the shape change is temporary. That means whatever shape change a body is observing or body is undergoing, it is just temporary. So on removing the load, it should regains to it original to its original shape. Okay, so what is this load here? It's a new term which we use. Load is nothing but we have to put something on my, you have to put some external force. As I said, that is my load. Okay, so if you apply some load on a body, it deforms, and immediately when you remove the load, what happens? It again comes back to its initial position. That's nothing but its original shape. Okay, plastic deformation. plastic deformation is something which explains that there is a permanent shape change. That means even after you remove the load, the original shape is not at all coming back. Okay, so that means the elastic deformation is temporary deformation where the original shape can be regained. Okay, temporary deformation, whereas my plastic deformation is permanent shape change or permanent deformation. That means even if I remove the load, okay, once after applying, the deformation is taking place. Even after removing the load, my original shape is not coming back to me. That's what plastic deformation tells me. Now, what is this viscoelastic deformation? So viscoelastic deformation is a non-linear deformation, firstly, and time dependent deformation. Now I'll explain this using graphs. Okay, so before knowing what are these graphs, we usually denote every graph in mechanical metallurgy or mechanical testing rather in stress versus strain curves or stress versus strain graphs. Okay, so what is stress? So we know that we apply some load on a body, so we'll see what is stress. So stress is usually denoted by sigma and strain is usually denoted by epsilon. Okay, there are many values of stress and strain like true stress, true strain, engineering stress and engineering strain, which we'll discuss just in a couple of minutes. But before that, we'll know what is an engineering stress. Okay, so let me put a suffix here, okay, of E. That means I'm defining my engineering stress and engineering strain. So these are nothing but my applied load divided by the initial area. Okay. My sigma E, that means my engineering stress, is my load divided by my initial area, whereas my strain is nothing but the change in length, the ratio of the change in length to its initial length. That means if I'm deforming from some L naught length to LF, then what I'll take LF minus L naught divided by L naught. This is my engineering strain. Okay, so these are the axes that I choose in order to explain these deformations. So how will they look like? Uh, Otherwise, I'll do one thing. So yeah, stress is on my y-axis and strain is on my x-axis. So again, I'm taking engineering values here. So yeah, we'll get to see what the true values is. Okay, so my elastic deformation. So I'm just loading it, removing the load, and what is happening? It is coming back to its initial position again. So this is a graph of an elastic deformation. That means to understand it better, it is going in here. Here we are removing the load, okay, and it is coming back in the same path. So my initial and final shape are the same in elastic deformation. So this is for elastic deformation, is also known as elasticity, the property of elasticity. Now, what happens to my plastic deformation? So plastic deformation is something where you can observe your permanent shape change, right? So here my initial and final point are the same, 1 and 2. But here what happens in my plastic deformation is that you will go like this, something like this, where you are seeing some permanent strain inducing in the body. That means there is some permanent shape change in the body. That usually, if I'm telling that my body is fracturing at this point, it tells me that it is my it's not F, that is my fracture strain. Okay, this is plasticity. Okay, we'll discuss more about this curve once we discuss about the different loading types, and then we'll come back. The other one is the other one is viscoelasticity. Viscoelasticity, as I said, is non-linear and also it is time dependent. So here if you see in elastic curve or elasticity, this is linear, right? The curve is linear, correct? Whereas here what happens is it is non-linear, it is going somewhere like this. On unloading, what happens is that it comes back to its original position but in a different path, okay, in a different path, and also take some time in order to come back. This is known as viscoelasticity. Best example for this is creep. Okay, we'll discuss all the mechanisms in our full course, but now this is an example to give. So this is viscoelasticity and the example is creep. So these are the different deformations. Now, as we set up the stress strain curves, one must know about the units of the stress and strain. What are the units? So usually P is nothing but my load, so it is the force applied, simple force applied, so that will be my Newton divided by let's say my length or the area of cross section is in meter square. Okay, that is Newton per meter square. This is usually called Pascal. Okay, so again, if you want to break it down, what is Newton? Newton is nothing but kg meter per second square. That is nothing but mass into acceleration, right? This is your force, correct? So from there, if you break it down, you will be getting Newton. Okay, so Newton per meter square is my Pascal, but the SI unit of my stress is MPa, megapascal, or which can be written as 10 power 6 pascals. Okay, or you can also write in another way by converting my Newton per meter into mm, that is 10 cube mm square, mm whole square. So what you'll be getting, 10 power minus 6, right? Newton per, oh, if you convert into this, what you'll be getting, 10 power minus 6 into mm square, but we are talking about mega, so into 10 power 6, so my SI unit will be Newton per mm square. This is the SI unit. So we can write the SI unit of stress in two ways. One is megapascal and one is by writing in mm square. So we just converted meter into mm and we multiplied that, so we got Newton per mm square. Now, what about the units of this strain? Okay, so I think you understood about stress. Now we'll look at this. So if you see, both numerator and denominator are lengths only. So you must observe that strain is a unitless dimension. That means strain has no units. Okay, this is an important thing that you have to remember. Now, now, uh, now that we have discussed about the deformations and the units of stress and strain, and also saw how the stress strain curves will be there, now we'll look at how the different loading types will be. In that, if you remember, the first one is tensile loading. So if I have a sample with me, tensile loading is a uniaxial loading which will be acting away from my body for elongating in the sense for stretching. Anything is the same, stretching the body. That is usually done in tensile testing. Okay, so this is sigma and some area or the dimension, how that will be changing. This will change something like this. Let me draw it. again. Okay, this is the final thing that I'll be getting. So what you can observe here is my length increases and area of cross section decreases. These are the two take homes from this test. So you can observe that that's why I thinned my final this thing. When this is final shape of the body. So you can observe that the length increases and the area of the cross section decreases. Now you must observe that what will be strain, engineering strain. So let's assume that this is L naught and this is LF. So LF minus L naught by L naught. So here what you can observe is LF is greater than L naught. So this strain is positive. So what you have to observe is the tensile strain is positive. Okay, this is about the tensile test where the area of cross section decreases and the length increases. We'll come back to this in tension test. Before that, quickly I'll just give an idea about the other two tests or two loadings also, that is compressive loading, where it is quite opposite to tension. Okay, so the forces will be just opposite. So for example, if I'm having some body like this, these are my compressive loads. For example, this is L naught. What happens to my final thing? This will be my final shape where this is LF, or maybe the area of cross section uh, can be also explained, but I'm just telling directly that the length decreases because the forces are acting in a compressive manner. That means we are pressurizing a body from two directions so that the area increases and the length decreases and the area of cross section increases. You can observe that clearly. Okay, so here if you see LF is less than L naught, so my compressive strain is negative. So wherever in any problem, in any values, if you see that the strain to be negative, you must know that it is a compression load. Okay, now the third and important loading type is shear, which is nothing but if I'm having a body, we are acting a tangential force. Okay, so usually it is denoted by tau. Actually the shear force is denoted by tau. So what happens if we do shear? It is just like the same thing which you do with a deck of cards, right? So if you just do apply a tangential force on a deck of cards, what happens? It tries to move away something like this, right? So this orange one is the final shape and the white one was the initial. So you can see the shear is the shear force is just sliding away my upper body with respect to my bottom body. That means just an example. Okay, so my shear strain will be equal to this theta. Okay, so usually if you write tan theta, what will be tan theta? That will be usually opposite by adjacent. Okay, so if you are just writing that my shear displacement is some x, okay, because of the shear force there is a displacement x. If you see what happens here, you can write it as x by, and if you take this to be some a, it will be x by a. So usually the theta values are very less small, so you can approximate this to be theta equal to x by a. Tan theta can be approximated as theta. Okay, this is what it is. Now one more thing you must observe in this is that shear forces are very much important in mechanical metallurgy, because all the atomistic scale problems will be like this. That means you will just compare this with two different plane of atoms. Okay, so like this. So for any deformation, for plastic deformation especially, the shear forces will help the atoms or the plane of atoms to move with respect to the bottom plane of atoms. Okay, so shear displacement is one important term which we'll discuss in uh, maybe in the full course. We'll be discussing about all the metallurgical fundamentals where we'll be looking at it. Okay, now one thing which I wanted to also discuss in this class, as I said, is about the tension test. Okay, so tension test is something which explains me about the how a material again will respond in a tensile load. Okay, in a tensile load. So what is elongation? We know the elongation of a material is nothing but the increase in the length, so that is done by the tensile load. So now we also saw engineering values, so we'll quickly see what is my engineering stress strain curve is explaining me. Then we'll go to true values. So this is sigma e, this is e, and as I said, my curve will look something like this. Okay, so if you observe here, my curve is going in a linear fashion and then converting into a curved path. Okay, so here we have some important takeaways that has to be noted. So here there is one guy, Hook. I think everyone knows Hooke's law, where he explains that the stress is directly proportional to strain. So where is it? In the elastic deformations or elastic regions only. So to remove the proportionality, we introduced a constant that is called capital E, where E is known as Young's modulus or modulus of elasticity. Modulus of elasticity. Okay. Now, if you see here, it is nothing but it is similar to some y equal to mx. So that is why we said it is only applicable in the elastic limit. So elastic region. So that's why the curve was linear here in this region. The curve is linear, right? As you can observe until somewhere here. So this is called as somewhere here is called as some in dash, and that a dash is known as proportionality limit. Okay, proportionality limit. So why we call it proportionality limit? Because stress is proportional to strain. Okay, but usually in experimental stuff you can observe that the elastic limit, elastic region is not stopping over there even after something somewhere here. Okay, that is a, we call it elastic limit. So what is the difference between these two? Elastic limit is the true limit until where the elasticity is there. That means why we are taking this proportionality limit is that experimentally to determine this elastic limit is very hard. Okay, because you can't differentiate where it is proportionality limit is gone already, right? You can see even after the y equal, this is like y equal to mx, right? But in this region this is not, but even then it is elastic region. So that's why it is very much difficult to experimentally evaluate that. So usually I mean, what you say, you usually take an equivalent site or equivalent point, that is proportionality limit. Okay, now other thing in this is the yield point somewhere here. Okay, which is my, I'm writing it as b. So b is my yield point. So what is this yield point? So yield point tells us in an engineering sense. So usually for all the engineering applications we want to know the differentiation between the elastic and plastic limit. Okay, which is very near actually. This a and b points are very much near if you observe. So we made some assumptions that okay, we want to tell that this is a plastic limit or plastic yielding is taking place. Yielding is nothing but plastic deformation is starting from there. Okay, yielding is nothing but plastic deformation itself. So how we have assumed yield point to be is that there should be some minimum amount of permanent strain in the body. Okay, that is about 0.2 percentage of the total strain. That means if you just draw an offset is nothing but drawing parallel to the elastic limit. That means I am loading my body, crossing the elastic limit, going over, and if I unload somewhere here at B, it should follow this path and take a strain of at least 0.2 percentage. Okay, remember it's in percentages. So this value somewhere here is 0.002 times the total strain. Okay, total is nothing but the fracture strain, which I already explained. Okay, that's the fracture strain. Now this is my yield point. As I said, this is totally for the engineering aspects. That means once a material is crossing the yield point, that means that there is a observable permanent deformation in the body. That's the thing. The next important point is somewhere here at the top. Okay, that is some C. Okay, as you can see in the curve, this is a point where the maximum load or the maximum stress is there. So it is known as ultimate tensile stress. That means ultimatum. It is the maximum point of stress in the curve. Okay, and next you can observe the decrease, and that D is finally the fracture point. Okay, so these are the different points. So now I want to talk more about this. So if you observe the graph, so we know that sigma is equal to load by area, right? But why this is happening? Why this thing is happening? Why my curve is going up and again coming down? So you have two different phenomena to explain that. Until my UTS, there will be something known as strain hardening taking place. What is strain hardening? So strain hardening is nothing but increase in the stress value because of the previous plastic deformation taking place. That means if you have some plastic deformation induced in the body, because of that plastic deformation, my stress required for my uh, total deformation increases. So usually it is denoted mathematically like this. Sorry for that. That is the change or the rate of change in my stress with respect to my strain. Okay, this is what my strain hardening effect. We'll discuss what are the reasons and all in the full course. Now what happens after UTS? So once a material is hitting the UTS, it means that it can't bear maximum load than that. We are talking with respect to the initial dimensions. First thing. So from here, there will be another phenomena called necking. So the stress increased because of strain hardening, but my stress is again decreasing because of the necking. Yeah, someone's asking some question. Yes, we'll take all the questions at the end. Okay. Now the part after the ultimate tensile stress is necking, and this necking is because of the localized reduction of area. Now, what is this localized reduction of area? So, if we have a specimen here, this is my initial thing. Localized reduction is something which happens like this. That means all the stress is acting here. It acts as a stress concentrator usually, or stress raiser, anything you can call that. Neck, it is known as neck actually. There are many criteria, necking criteria and all. Yeah, we'll discuss that later on. So because of this reduction in area, you can observe that it will be not able to withstand high loads and it drops down the stress it can take, and finally fractures. Okay, this is what space. This is the um, important phenomena, that is strain hardening and necking, that will be taking place in my material after yield point. Okay, now as I said, tension test will be usually done for this. And brittle material, what is ductility and what is brittle? I want to also explain this here. So as I wrote in the property, ductility is an important property that we can deal with, right? So this brittle and ductility, how the curve will be there. Ductility is nothing but the material is said to be ductile when it is undergoing some plastic deformation before fracture. That means we just saw the curve, right? Before fracture, there is some, this is my yield point, this is my plastic strain. That means there is some permanent shape change, permanent deformation. Whereas in brittle, without any plastic deformation, it fails. Okay, it fails here itself in its elastic limit. So ductility tells us about the property of a material, which is telling about the plastic deformation. Whereas, fracturing after some plastic deformation. Whereas brittle materials are something which fail or which fracture before any plastic deformation itself. Okay, that's the difference between these two. One more thing is important to think about is the Young's modulus, that is E. So if you see in the elastic limit, what is the Hooke's law? Sigma equal to E into epsilon, right? So this is nothing but the slope of the curve, correct? Y equal to mx we just compare with. So the slope of the curve gives us the elastic modulus. So this elastic modulus tells us about the resistance to deformation. Resistance to deformation, that means if the slope is high, so if, for example, I'm just drawing one more curve in this to explain. So I want to have some constant, well, where is this? I want to induce some constant strain here. Okay, some sigma 1 or something. So I want to induce this strain. So if you see here, which material, blue colored line or yellow colored line, which one is having more thing? Okay, which one is having more stress? In order to produce sigma 1, this is here only sigma blue, and this is going up till here. That means if you have more slope, obviously you will be having more Young's modulus. That means if you have more Young's modulus, you will be going to see more amount of stress required even to produce less strains. That is what it is. Okay, so this is an important parameter. Young's modulus or modulus of elasticity is an important parameter which tells us about the resistance to deformation, which is nothing but the stiffness or rigidity. Okay, stiffness is coming from here. The resistance to deformation is telling us about the stiffness, how stiff the material is. That means how resistance the material is providing for deformation, that means for shape change. Okay, that's what it is. Now the last topic for today, and then we'll go to the properties and I'll explain how we got that, is the true values. So we saw engineering values till now, right? So I'll just write down here what are the engineering values. That is P by A naught, as I said, initial area, and epsilon E is my delta L by L naught. Okay, I just wrote L as minus L as delta L. Okay, now what are the true values? So true values gives us the values at that particular point of time instantaneously. That means if you want to know some value at that particular instant, what is the stress, that means you have to use the instantaneous values. instantaneous values of what? Anything, load, area, length. Okay, in order to get that. Fine. So what I meant by instantaneous values is that if you want to calculate the true stress, you have to take the load at that particular, for example, at a point B I want to calculate, I have to take the load at that point divided by what I want to take the area of that point. What is the area? Because we know the area is continuously changing, right? Area is decreasing as we saw in tensile test. So this is what it is. So we have many formulae for that. We'll just also derive the relationship between that and this. Okay, whereas true strain will also be that only. Okay, so for example, if I want to lb minus at that particular instant something la by la. Okay, you must not take the initial value, but just before that strain you have to take it. This is true strain. So this is mathematically difficult to calculate from this. So how can we relate the true stress and true strain? And then we'll also look at the true curve. Okay, true values curve. So here what you can write, for example, true strain, if you write like this, some load p divided by ai at that particular point. Okay, and this also can be written as integration of dl by l from 0 to here. Why we took this is because we know that the strains, the small part of strain. Okay, if you divide the whole test as 10 minutes and you divide into 30 seconds interval, you can write like this, right? dl1 by l0 plus dl2 by l1 plus so on. So that only we wrote it like this as integration. So from that what we can get, as I just wrote, it is d epsilon 0 to this. So this will be nothing but okay. From this we got this actually. Okay, we just integrated the whole part and we know what are the values, so we took back here. So we know something dx by x, integral dx by x is, what is dx by x? Ln of x. So here we have l. So the limits are in terms of l. Actually if you write in terms of epsilon, we have 0 to epsilon t. In terms of l, what will be initial to final? Okay, l naught to lf. So I'll just put it the limits and we have ln of f by l naught. Okay, so I directly wrote it. Actually what we get it, ln of lf minus ln of l naught. So lna minus llb is ln of a by b. Okay, so we got the value of true strain as this thing. Clear? We got this. Now we must also know about volumetric strain. So what is volumetric strain? So in elastic deformation, usually we call it delta. In elastic deformation, if I'm taking delta E, it will be 0. Okay, sorry, in elastic deformation, just a minute. In elastic deformation, it will be the sum of strains in all the directions, whereas in plastic deformation, it is 0. Okay, for all this derivation, you must be joining our full course to know about everything in detail. Okay, so now I just directly took the values. Now what I can write, if the volume is constant, yes, if volume is constant only, my volumetric strain can be 0, right? That means how I can write my volume? I can write into area. I can write as area into length is equal to some constant k. That means initial area a naught into l naught, initial length equal to final. So this I can write as lf by l naught will be equal to what? A naught by af. So I'll just replace it here, because usually instead of lengths the cross sections can be determined from this, right? So ln of a naught by af. So if you write area as pi by 4 d square or whatever, pi r square, right? Cross section, if a circular cross section is there, pi r square is there. So from diameter you can write it as 2 ln of d naught by df. I just substituted. Okay, it's a simple math. You have to just substitute area as pi d square by 4 or pi r square. Okay, if I took d actually diameter. Now here to calculate, so we got the value of true strain. Now we are interested to calculate true stress also. So this is easy. So just multiply and divide by a naught. Okay, so what we'll be getting, just separate p by a naught into what we are left with, a naught by ai. Ai is nothing but at the final thing I can take it af, right? Because we are considering from initial to final, so I can do that after the final thing. That's af. So what is a naught by f? Again we know that's lf by l naught. Okay, or okay, I'll just write it that, and then into a naught by af is lf by l naught. Okay, so from this what you can write, you can remove the log, so lf by l naught will be equal to um, it will be actually 1 plus ee. How? Here, from here if you write lf minus l naught by l naught equal to the engineering strain, so just divide it, you will be getting lf by l naught minus 1 equal to this. So take that minus 1 to the other side, so what will be getting, lf by l naught is equal to engineering strain plus 1 into what is this, p by a naught. P by a naught is my engineering stress. So this is my true strain and this is my true stress. Okay, so we have calculated both the values with the help of basic mathematics. So these are the true values. Now how will the graph look like? So this is the last topic we'll deal in today's lecture. So this is true values. Okay, as you see, I changed the curves. So my true values will always go up. My true values will always go up continuously. Why? Because if you see the math and all, you will be getting this. Okay, so here somewhere you'll be getting a yield point, here you'll be getting the maximum, that is UTS and all. So if you compare with the other one, that will be like this. Okay, somewhere like this. That means my true stress versus true strain curve is always above and to the left. Okay, so you can see it's to the left of the engineering curve. This is an important part you have to remember. Okay, of the engineering curve. Now there should be some equation, right? We usually try to fit in some math equation into a curve. That's called curve fitting, right? So usually we have flow. This is known as true stress to true strain curve, or it is also known as flow curve. So for the flow curve, the equation is sigma is equal to k into epsilon power n. Sigma equal to k into epsilon power n. Now what is this k and n? So we have k to be my strength coefficient and n is the strain hardening coefficient. Okay, you know what are these are the true values actually. Fine, so if you apply log on the both, you will be getting this thing which is known as, this is known as Holloman equation, right? This is the flow curve, right? So with this I have explained some of the basics of the tension test and obviously all the curves used. So now we'll be going to my properties which I wrote over here in the starting. Yeah, strength. So how can we get all this stuff? So strength, we can, according to one's requirement, you can choose yield strength or ultimate tensile strength. Okay, or the fracture strength. It depends on the application, on the requirement that you are choosing. So strength can be derived from the stress strain curve. Stiffness, as I already said, stiffness is the resistance to deformation, which comes out from the value of my Young's modulus. Ductility. Ductility, we also know that the amount of plastic deformation that is taking place in the body. That means ductility is explained by the total strain or the fracture strain of your body. And yeah, fracture. Again, fracture, we can easily identify at what stress, after how much strain my fracture will be taking place. So this is how my stress strain curve is helping me to calculate or to study about the important mechanical properties, right? So with this, I think it's about 50 minutes. So we'll stop for today.